Earlier, we looked at our camshaft specification card. We concentrated on this end of it, which told us which lifters, which springs, retainers, and locks to use with our camshaft, and also it gave us the installed height of our springs and the required pressure of the spring at that installed height. Now we're going to take a look back at the actual timing events section of the cam card, which gives us all the information we need to properly degree our camshaft. Also, please note and remember that all readings will be taken at 50 thousandths cam lift. We're going to concentrate on just this portion of the card, which is the intake lobe portion. We've taken liberty of removing this section of our card and putting it on the front of the block to make it more easy for you to follow what we're doing. This is what degreeing a camshaft looked like. We have a large diameter degree wheel to make our readings more accurate. We have a very steady pointer. We're using two dial indicators, one for top dead center of a piston and the other for cam travel. This can be accomplished with only one indicator, but it's much easier with two. Let's take a quick view at the lifter portion of the block. What we've done here is we've taken a stock lifter, we've removed the top out of it and the insides, we machined a piece of Teflon and pressed it into the lifter body. This gives us a nice extension to work our dial indicator off of. You could also use a dial indicator with an extended post. We found this to be a little better because the thin extension on the dial indicators aren't that accurate. This is much more substantial. Also, you want to line up the dial indicator as perfectly in line with the assembly or the lifter as possible in both planes, this way and this way, to obtain greater accuracy in reading off of the cam lobe. We've already mentioned the use of a large diameter degree wheel. We do that because the larger the diameter degree wheel, the more spacing there is between each degree, makes it easier to read and less confusing, less chance of overlapping your readings. To mount the degree wheel properly, we took a factory harmonic balancer, removed the outer ring, opened up the inside dimension of it slightly so that it just slides over the crankshaft. Now we can bolt the degree wheel onto this hub with a plate that we welded a large nut to. This assures us that the degree wheel will not slip on the crankshaft and give us false readings. Reinstalled our degree wheel, and also note the large wrench. The longer the lever you use, the easier it is to control the movement of the piston and the crankshaft to get easier readings on your dial indicators. What we've done here is we've mounted a dial indicator on the deck surface of the block, and we mounted the stem of the indicator perpendicular with the bore. What we're going to do now is locate our top dead center of number one piston. So now what we have to do is rotate the crankshaft around until the dial indicator stops moving as the piston comes up. We want to move this slowly once it starts moving. And we're going to take notice of where the indicator stops at its highest reading. It just went up to the highest reading and then back off. So now we have to back off beyond that and come back into it in crankshaft running rotation, which as you're viewing is clockwise. Coming up very slowly, we're going to stop right at the point was the highest reading on the indicator, which is here. We're going to reset our indicator dial to match the 0 up with the needle. Now we have to set our indicator, our pointer on the degree wheel at the top dead center mark. Now we'll double check to see if we arrived at true top dead center. To do this, we're going to turn the crankshaft once again in direction of engine rotation, 50 thousandths travel on the dial indicator, which would be one full revolution. So when the needle comes back to 0, we'll stop and read our degree wheel. reading our wheel, we'll note we're at 12 degrees. Now we're going to reverse direction of the crankshaft, bring our dial indicator back around to 0. Now we're going to continue counter rotation until our dial indicator has reached 0, which is 50 thousandths travel, and go beyond by about 20 or 30 thousandths. This way, to get our reading back at 0, which would be 50 thousandths of counter rotation travel, we'll be reading it in proper rotation of the engine running mode, which will ensure us greater accuracy. We'll note now we're at 12 degrees on the opposite side of top dead center. Due to the fact that we're 12 degrees before and after top dead center at 50 thousandths travel the piston in both directions tells us that we had located true top dead center in our earlier attempt. So we'll move back to top dead center on our degree wheel, which will bring us back to 0 on our dial indicator. At this point, we've double-checked the fact that we have arrived at true top dead center of number 1 piston. Now, we can use our other dial indicator along with the information on our cam spec sheet to degree the cam. Now, let's take a look at our camshaft specification card. If you note, it tells us that the center line of the intake lobe should be set at 160 degrees in relation to crankshaft rotation. In order to check this, we're going to continue to rotate the crankshaft in a running direction, which would be clockwise as you're viewing, and note the lift of the intake lobe at its highest point. At that time, we're going to take a reference reading 50 thousandths on both sides of the lobe lift and record the amount of degrees indicated on the degree wheel at both locations. We'll then add these two numbers together and divide by 2. If the quotient turns out to be 106, that means that we have arrived at 106 degrees of crankshaft rotation on the center line of the intake lobe. However, if our quotient turns out to be, let's say, 110 degrees, it's indicating to us that the camshaft is 4 degrees retarded from our desired 106 degrees. We'll have to compensate by advancing it with a 4-degree bushing. Consequently, if our reading was, say, 102 degrees, it tells us that the camshaft is advanced 4 degrees too far. We'll have to be retarded with a 4-degree bushing to arrive at our desired 106 degrees. Let's do this now. We're going to continue rotating the crankshaft in the running direction, watching the dial indicator we have on the cam lobe. We want to stop when the dial indicator reaches its highest reading. It's coming up now, and we'll continue crankshaft rotation until the needle stops. That will be the highest point of travel of the cam lobe. The slower you go, the more accurate this will be. We've arrived at that point now. Now we can reference the 0 mark on our dial with the needle. We're going to continue rotating the crankshaft in the running direction now until we arrive at 50 thousandths movement. Also, please note that this dial indicator, unlike our previous indicator, registers 100 thousandths per rotation. So 50 thousandths travel will be halfway around the dial. We've arrived at 50 thousandths travel. We're going to look at our reading on the degree wheel. We'll notice we're at 147 degrees. We'll write this down. Now what we have to do is change direction and counter-rotate the crankshaft back to 0, which is the high point of our cam, and continue just like we did when we were trying to determine top dead center, past our 50 thousandths reading, and beyond by at least 20 to 30 thousandths. Changing direction again, we'll come back to our 50 thousandths mark. And once again, we're going to record our reading on the degree wheel. At this time, we're at 62 degrees on our wheel. Dividing the sum of these two readings by 2 gives us 105, which means we're 1 degree within our 106 degree desired. Being within 1 degree is very acceptable, and we'll leave it the way it is. We've removed the degree wheel to expose the fact that we're using a Pete Jackson dual idler gear drive on our camshaft. It consists of the crankshaft sprocket, the dual idler assembly, which is free floating, and the cam gear. The cam gear utilizes centered and offset bushings on the camshaft dowel pin to adjust the degree of its installation. Over here, if you take a close look at these 4 bushings, you'll notice that the hole is offset in them. This is a 2 degree offset bushing that looks fairly centered. The 4 degree offset bushing, you notice, is a bit heavier on the bottom and thinner on the top. Consequently, the same thing with the 6 and the 8 degree bushing. These bushings can be installed to either advance or retard the camshaft to the degree that's designed in them. When degreeing a camshaft using a timing chain assembly as opposed to a gear drive, everything in the procedure that we showed you before in the gear drive is the same, including the rotation and counter-rotation methods we showed you. The only thing that is different is the means of making a timing correction. We have 3 means available to us. 1, if we modify the cam gear, we can use the offset bushings as we did in the gear drive, or we can opt to use offset keyways between the crank gear and the crankshaft, or we can use an indexable crank gear which has more than 1 keyway in it, which allows us to alter the timing of the camshaft. Take a quick look at what's happening here. This is play that's built into this gear drive system. You also have similar type of lash play with a timing chain. It is because of this play and lash that you always have to go beyond your 50 thousandths reading when you're counter-rotating and then come back to your 50 thousandths reading in order to absorb this lash and place the gears or your timing chain assembly in the simulated running condition. Otherwise, your readings will be very far off. Notice on the dial indicator, as I run through the lash of these gears, we're monitoring 8 thousandths change. This will very seriously affect the readings on your degree wheel. So always go beyond your 50 thousandths movement when counter-rotating by about 20 to 30 thousandths movement, and then come back to your 50 thousandths reading to get accurate results. On our Pete Jackson gear drive, they supply us with a lock plate and a cam button. All you need to do is install the cam button, place the lock plate over it, put the washers on our bolts, put the bolts back in, torque them to approximately 18 foot-pounds as per instructions from Pete Jackson. And once they're torqued in place, bend the lock tabs over the flank of the bolt. This is the way your assembly should look with the lock plate properly installed and the tabs bent over the bolts very snugly. Be very careful when tightening these bolts down if you're using a socket that the socket doesn't put side load between the bolt head and the cam button where you could destroy it. Also, once the lock tabs are positioned in place, be very certain that the end of the tabs don't project over and touch the cam button. If they do, the tabs must be slightly trimmed to make sure they do not contact it. At this time, the camshaft installation is complete.